Yeah, thank you for the introduction, and then good afternoon, everyone, and welcome to this presentation, the topic of which is tribomechanical fracture analysis of additively manufactured TI-64 under cyclic loading. The additive manufacturing process in question is selective laser melting, in which metal powder is first deposited on a build platform, and then a single slice of the part is created by a laser. Afterwards, the build plate moves down by a layer, and the coater spreads a new layer of the powder on the build plate, which is subsequently melted by the laser again. Now this process repeats until the entire part is finished. So it's clear that the additively manufactured, the process of additive manufacturing can offer numerous benefits, like the decreased material waste or higher design freedom, which, for example, enables creation of such complex cooling channels in turbine blades. But before additively manufactured parts can be used in such safety critical applications, we have to make sure they're safe to use. And then sort of a motivation behind my research, in which I'm investigating the impact of threading fatigue on the structural integrity of additively manufactured TI6AL4V components. Now, in this presentation, I will first give a very brief introduction to threading fatigue, and I will go over the experimental and numerical methodology. Afterwards, I will present some of the results that I've obtained so far, and I will finish the presentation with a short conclusion. So starting with a short introduction to threading fatigue, it occurs due to changing external forces, for example, caused by changes to the RPM of the turbine engine, or due to vibrations, and those generate cyclic contact forces and also relative displacement between two parts under pressure. In this case, it's the blade and the disc in a turbine assembly. Now, the most damaging condition takes place when slip occurs at the edges of contacts, but we have a stick condition in the middle, and this results in a significant damage to the contacting surfaces, which is greatly detrimental to their fatigue lifetime. Now, threading fatigue can be a challenging phenomenon to study, and it often requires experimental and numerical approach. In the next few slides, I'll go over the methodology I used in my research, starting with the selective laser melting process itself. So the material in question, TI-64, the parts were manufactured using 3D Systems Pro X 320 metal printer. The density of the final components is equal to 99.6% of the theoretical density of around 4.4 grams per cubic centimeter squared, cubed. After the printing process, the parts underwent standard heat treatment at 850 degrees in argon atmosphere for 2 hours, and were later cut to the final dimensions using wire EDM, which resulted in a final surface roughness of array value 0.9 micrometers. So in this presentation, I will mainly focus on the results of the dovetail blade setup shown here in the middle. But first, just a few more words about the material properties. So here we can see the stress strain curves of the wrought and the additively manufactured material. So as you can see, the additively manufactured TI-64 has both lower stiffness and lower yield and ultimate tensile stresses than the wrought material, but it has somewhat higher ductility. The strain before failure is higher, as you can see here. Now, the microstructure is also pretty standard for additively manufactured TI-64 that underwent heat treatment below its beta transit temperature. So the columnar prior beta grains are still relatively clearly visible, and the microstructure consists of a mixture of lamellar alpha and beta phases. Now the experimental setup is shown here on the left. So the stainless steel fixture holds threading pads, which are made from wrought TI-64, and those represent the disc in the turbine assembly. Now, the application of a cyclic fatigue load to the sample generates cyclic forces in contact and cyclic relative displacement between the sample and the pad, which creates fretting fatigue conditions there. The geometry of the sample is also shown here. The most important part here is probably the skew angle, which is chosen to be 35 degrees. And also two different fretting pad geometries were considered in the study. So one with cylindrical contact edge, which results in incomplete contact, and one with flat contact edge, which results in a complete contact. So the setup was also recreated in the finite element software in order to study the stresses in contact in more detail. A convergence study revealed that the minimum mesh size should be 10 micrometers, and the used coefficient of friction was equal to 0.55. Now, if we look at the principal stress contour in the dovetail portion of the sample, we can see that there is a stress concentration at the edge of contact, but there are also high stress or principal stress fields at the curved edges as well, which is important to keep in mind. Now, if we look at the stress distribution at contact, we can see that, again, the maximum load, the peak in the tangential stress is at the edge of contact, which likely drives the crack initiation there. And the tangential and shear stress distributions both reveal a stick-slip condition with stick in the middle and slip at the sides. So is the most damaging condition, the most critical one to study. So that about covers it for the most important aspects related to methodology. And I'll start the results section with some results of the DIC analysis of the dovetail joint setup. So it was primarily performed to evaluate the symmetry of the setup and the quality of the alignment of different parts before starting the test. But in one case, the DIC analysis was repeated after 1,000 loading cycles and after 100,000 loading cycles. So the test was stopped, and then 2 loading cycles were applied slowly while taking pictures for the DIC analysis. So, and here we can see the results of that. The figures show the vertical displacement of the sample and the pads. So we can see that at the minimum load, there is some asymmetry in the sample, but at the maximum load, there are no such abnormalities. So when the stresses are the highest, the setup is symmetric. Now, those results were also later used to determine the coefficient of friction. Could be used in finite element simulations. So displacement fields were extracted from the areas close to the contact edge and then transformed to align them with the direction of relative displacement. Now, initially, the values of slip are quite different. And even though after 1,000 cycles they become closer to each other, they're still quite high. So it's very likely that we are still dealing with some initial running in phenomena. And only after 100,000 loading cycles, we can be sure that the setup is in a stable condition. And we can use those slip amplitude values to calibrate the coefficient of friction in our finite element model. So this was done by performing a parametric study with different coefficient of frictions and extracting the displacements in the same region in the very much the same way as in the DIC analysis. And that resulted in a coefficient of friction equal to 0.55. Now, moving on to the overview of the experimental results, the lifetime of tested samples are shown here on the figure on the left. Now, if we focus on this region, we can see that the performance of the additively manufactured TI-64 is somewhat worse than the rod material, but this comparison is made a bit difficult due to, say, large scatter in the rod data and also a number of samples that failed outside of contact. So for the rod material, it was mainly a failure at the curved edge. For the additively manufactured material, the failure also occurred at the neck here, or the transition zones, but I will talk about it more in a second. So in order to better gauge the response of the additively manufactured TI-64, well, in compared with the rod material, data from literature was extracted as well and is plotted here. It's for the same dovetail setup and also the same material. But comparing it using force is not very representative. Since we're dealing with different contact geometries, different sample geometries as well. Therefore, those models were recreated in finite element software to use more local parameters for that comparison. But that came with its own set of challenges, as a lot in a lot of the past research, the tests were done at say very high stresses far into the plastic region, but that wasn't really addressed in that research back then. So instead, another critical threading fatigue parameter could be used for comparison, and that is the slip amplitude at the contact edge. So, say based on this comparison, the AM material appears to be say stronger than the conventional one, but we can take this comparison a step further and include the properties of the material, like the yield stress and the stresses at the contact edge, into a sort of a damage severity parameter, which modifies the slip at the edge into the effective slip. So by looking at this graph, we can say that the response of the additively manufactured material under threading fatigue conditions is similar to the rod one. Now, if we go into more fractography and details of some of the tests, so here we can see a good example of a threading fatigue condition. So the stick and slip areas are clearly visible. We can also see a crack which resulted in a failure that is present right outside the slip area. Also, interestingly, we can see a secondary crack on the other side, which initiated there, possibly here at the edge, but haven't had the chance to propagate since the failure occurred on the right side. If we look at the crack surface, we can distinguish two, say, likely areas where the crack could have initiated. So it's possible that the crack started growing in from two regions and later coalesced into one big crack, which caused the failure of the specimen. Also, interestingly here, since here we can see the contact area at relatively high angle under the SEM, we can clearly see the difference between the slip and the stick areas in threading fatigue. Now, as I said, a number of AM samples failed outside contact, like this one, which failed at the transition zone between the curvature and the flat portion. So further analysis revealed that the presence of large internal defect, which acted as a stress concentration, caused this early failure due to plane fatigue. So the globular particles you can see here are likely particles of unmelted powder and point to the origin of the defect as a lack of fusion defect. So if we look at the other side of the surface, we can see the other defects more clearly. So here likely the crack initiated here and quickly propagated to the edge of the sample and also to the other defects, resulting in a rapid failure of the specimen. Now higher magnification pictures of the critical defect show more of the not fully melted globular particles and highlight just how deep the defect is. It reaches multiple layers into the material. And some details about the defect. So the approximate surface area is 0.8 millimeters squared, and the equivalent circle radius is 0.5. The defect is quite irregular with the circularity of 0.77. So for comparison, the circularity of a square is 0.7. I think I'm running out of time, but I'll go quickly over the next few slides. So this is another example of a defect out of a failure out of contact that occurred due to internal defects. But in this case, the threading fatigue crack managed to say initiate, but didn't have time to propagate, and the failure occurred here in the neck area. And the similar story with the last sample that failed outside the contact area. Now, also, just a few more words about the finite element simulations or the modeling campaign that accompanied the experimental results. So the continuum damage mechanics model was used to try to estimate the lifetime of the dovetail joint additively manufactured TI-64 components. So this was used specifically for the initiation lifetime, but also the propagation path and lifetime were studied using the XFEM technique. So here we can see that up until 2 millimeters, a quite good agreement is reached between the simulated crack propagation path and the experimental observations. But after that, there's some deviation, so there's still some improvement that can be done there. And here you can also see the results of the predictions. So again, here we can see quite a good match with the experimental results, but this is performed on a very limited set of data. So further studies are required. And that brings me to the conclusion and the future work. So the fretting fatigue response of AM-TS64 is highly sensitive to surface and subsurface defects. Yeah, it's entirely possible for the crack to initiate in the fretting fatigue region, but the failure can occur outside due to internal defects. And yeah, the next step would be to incorporate such subsurface defects in the finite element simulations and yeah, see how it will affect the lifetime and the stresses inside the sample. And yes, that brings me to the end of the presentation. Thank you very much for your attention.